Chapter 11, Part 4, Continuity. In this lesson, we come back to an idea that I actually established at the very beginning of the chapter, but I didn't actually use the word continuity. A function is continuous at a point if three conditions are satisfied. First, the limit has to exist. Second, the function has to exist. And third, the limit has to equal the function. If the limit exists, if the function exists, and they exist at the same point, we call this a continuous function at that point. Now, if you recall this little statement right here, this is what I used when I called something a well-behaved function. And now I can more clearly define what I mean by a well-behaved function. A well-behaved function is a continuous function. I just use those words interchangeably. I just didn't want to use the word continuous early on in the chapter, so I just called it well-behaved. Those functions that we grew up with in Algebra 1 and Algebra 2, all those smooth, fully connected functions, that just means continuous. But here I'm just going a little bit deeper into that idea of continuity. The limit has to exist, the function has to exist, and the limit and the function have to agree on where they exist. As long as all three of those conditions are satisfied, then we can call it a continuous function. So let's look at where a function is not continuous. At what values of x on the interval 0 to 4 is the function not continuous? Well, let's just go down the list. Step 1, the limit has to exist. Well, if I look right here, at x equals 1, we have a problem. The left hand is going to 0, the right hand is going to 1. Therefore, at x equals 1, I have a discontinuity because step 1 of my continuity definition isn't being satisfied. The limit does not exist. Right here at x equals 2, the limit exists. Both the left and right hand side agree that we're going to 1. So step 1, check. Limit exists. Step 2, the function exists. Well, we have a dot up here at x equals 2, so yes, the function exists. Step 1 and step 2 of my continuity definition are satisfied. But part 3 of my definition, does the limit and the function agree? In fact, no, they don't agree. The limit is going to 1, the function is at 2, therefore at x equals 2 we also have a discontinuity. If we look at x equals 3, I can see that the limit exists, both sides are going to a height of 2. The function exists, plug in x equals 3, the height of the function is y equals 2. And the limit and the function agree. Both agree that the limit and the function are at 2. So this would be an example in any one of these points right here, or right here, or right here, would all agree that the limit and the function are equal. The only points at which the limit and the function are either non-existent or not equal would be at x equals 1 and x equals 2. In other words, if I see any breaks, holes, or jumps in the graph, we have a point of discontinuity. So as easy as it is to identify continuity and discontinuity based on a graph, we can do it based on a function as well. Here we're going to look at 3 different types of continuity problems. Here I'm going to have a polynomial function, a rational function, and then I've got a couple examples of piecewise functions. Let's start with the first one. Is the given function continuous at the given value of x? Explain. So here we have a polynomial function at x equals 2. And this one basically comes down to background knowledge. Yes, I could go through the 3 steps of my continuity definition, check off each one. If each one is true, then I know that it's continuous. Or I can just use my knowledge of polynomial functions. I happen to know that f is a polynomial. By observation, I can look at f and see, yes, this is a polynomial. I also happen to know that part of the definition of polynomials is that their graphs are smooth and continuous. The fact that f is a polynomial and polynomials are continuous, I can jump to the conclusion that f is continuous at x equals 2 because f has to be continuous everywhere. But of course, I could still use my definition of continuity to simply imply that it's continuous by saying the limit as x approaches 2 of f of x is equal to f of 2. If I applied the limit to this function, I would get an answer. If I plugged in x equals 2, I would get the same answer. So whether I go with this route or this route, polynomial functions are always continuous. So if I ask you, hey, is this polynomial continuous at this point? The answer is always going to be yes. Similar process with rational functions. Rational functions are continuous everywhere except where there's a domain restriction. So because rational functions are continuous within their domain, I just have to check, is x equals 3 within the domain? Well, I know for rational functions, domain restrictions occur based on the denominator. The denominator is x minus 1, therefore the domain is x is all real numbers except 1. Well, x is 3 is the question I'm asking about. So since x equals 3 is within the domain, I can say yes, it is continuous because x equals 3 is within the domain. Again, though, I could just use my definition and say limit as x approaches 3 of f of x equals f of 3 and say it's continuous because this is satisfied. The limit exists, the function exists, and they're equal to each other. The point at which I really want to get into using the full definition of the limit is when I'm looking at piecewise functions. With piecewise functions, I'm going to go through each step of the process to determine if this function is continuous. I'll start with step 1, see if that's true. Step 2, see if that's true. Step 3, see if that's true. If all 3 steps are true, then I can say that it's continuous. So starting with, does the limit exist? Well, to determine if the limit exists, let's look at the left hand and right hand. So step 1, to determine if the limit exists, I'll look at the left hand, right hand, one at a time. So for the left hand, I'll look for x less than 1. Plug in 1. 2 plus 5 is going to give me 7. So the left hand limit is going to 7. The right hand limit, plug in 1 to this guy, I'm going to 8. So here's a situation where the left hand is going to 7, the right hand is going to 8, therefore the limit does not exist. And at this point, I can stop. Since the limit does not exist, I know that f is not continuous at x equals 1. We're going to have a break in the graph, the function is not continuous. So using that same technique, why don't you go ahead and give this one a try. Pause here, hit play when you're ready. Again, continuity is a 3-step process. Step 1, does the limit exist? Well, let's look at the left hand, right hand. For the right hand, we'll use this guy. Negative 2 plus 14 is going to give me 12. For the left hand, we'll use this guy. Negative 2 squared is 4. 4 times 3 is also 12. The left and right hand agree, so the limit does exist, and the limit is 12. But remember, that's only one part of our definition. Part 2 of our definition is to determine, does f of 2 exist? Well, the fact that I have an equal sign right here says that yes, f of negative 2 does in fact exist, and I can plug in negative 2 to determine that f of negative 2 is 12. Step 1 is satisfied, the limit exists. Step 2 is satisfied, the function exists. Step 3, does the limit equal the function? Well, yeah, 12 and 12 are the same number, therefore f is continuous at x equals negative 2, since the limit is equal to the function value. Alright, now let's go a little bit deeper into the concept of discontinuity. Discontinuities exist in 2 main types: removable discontinuities and non-removable discontinuities. Removable discontinuities are holes. Essentially, if I have a hole, I can fill in that single point and remove the discontinuity. So if I see a hole, it's a removable discontinuity. Another way of thinking about it is if the limit exists, it's a removable discontinuity. Remember, limit existing is only one step of the continuity definition. So if the limit exists, but in this case the function does not exist, this is a discontinuity because step 2 is broken, but it's removable because step 1 was at least satisfied. Here's a situation where the limit exists, the function exists, but the limit doesn't equal a function, so it's a discontinuity, and it's removable because step 1 was satisfied. It's a removable discontinuity because the limit exists, but another part of the definition was broken. Non-removable discontinuities are jumps and asymptotes. So with jumps, the limit does not exist. With asymptotes, the limit does not exist. So a non-removable discontinuity is where the first part of the continuity definition is broken. If the limit exists, we have a removable discontinuity. If the limit does not exist, we have a non-removable discontinuity. Removable, again, I can just fill in one point and remove the problem. Non-removable, it wouldn't be just one point that I would have to fill in. I would have to move an infinite set of points to remove that problem, and I'm not going to take all the time to move an infinite set of points. Asymptotes, there's no connection here. There's no way I can just fill in one point and fix the problem. Holes are removable, jumps and asymptotes, non-removable. Limit exists, removable. Limit does not exist, non-removable. I can look at this algebraically as well. Here's an example of a function that has a discontinuity. In this case, we have 2 discontinuities. x equals 4 and x equals -3, those would be domain restrictions and thus also discontinuities. But notice for x minus 4, it would cancel out. In other words, I can remove x minus 4, making x equals 4 a removable discontinuity. Also, by the techniques that we learned way back in Chapter 2, it's a whole because I was able to remove it. Removable, whole, limit exists. If I look at this piecewise function, notice to the left I'm going to 2, to the right I'm going to -2. So again, this would be an example of a jump where the limit does not exist, making it non-removable. Or that same function, but instead of focusing on x minus 4, x plus 3. I'm able to cancel out, I'm able to remove the discontinuity at x minus 4, but I'm not able to remove the discontinuity at x plus 3. So we have a vertical asymptote at x equals -3 because it was unable to be canceled out. I was unable to remove it. So let's look at this function right here. I want you to identify and describe the discontinuities. I think you've got enough information to go ahead and try this one on your own. Pause here, play when you're ready. All right, we're going to start by identifying the discontinuities. It's a rational function, so I need to know when the denominator equals 0. Before I can do that, I'm going to factor everything out. The top is a difference of squares, x plus 2 minus 2. The bottom factors into x plus 2, x minus 3. So that tells me I have two discontinuities at -2 and +3. What I have not yet determined is whether those discontinuities are removable or non-removable. Well, that comes down to, do they cancel or do they not? X equals -2 comes from the x plus 2 factor, which cancels out, making it removable, whereas x minus 3 is not going to cancel, non-removable. And yes, it's just easy as that. Why don't you give this one a try on your own? Pause here, play when you're ready. Just like before, we'll start by factoring everything out. The top factors into x plus 6, x minus 1. Bottom we don't have to do anything with, but that tells me I only have one discontinuity at x equals 1. And since it cancels with the x minus 1 on top, that makes it a removable discontinuity. All right, what about a piecewise function? Remember, with piecewise functions, the key comes to, does the limit exist? Does the left hand equal the right hand? So I'm going to focus on that. The left hand limit is going to go to -3. The right hand limit is going to go to 7. So here we have a situation where the left hand does not equal the right hand, meaning the limit does not exist. And the fact that the limit does not exist means it must be a non-removable discontinuity at x equals 1. Now remember, as easy as it is to identify and describe discontinuities based on functions, it's even easier to do it graphically. Go ahead and give this one a try. Play when you're ready. All right, just by observation, I can see that I'm going to have 1, 2, 3 discontinuities. So I have discontinuities at -2, +1, and +2. Focusing a little closer on -2, I see I have a hole, but the limit exists, which means it's removable. At x equals 1, I have a hole up here, but I have a closed dot down here. The point is I have a jump. Jumps are non-removable. At x equals 2, asymptote. Asymptotes are also non-removable. Now here let's look at a different type of question, one of my favorite types of questions. Hint, hint, nudge, nudge. Find the value of a that makes the function continuous. So in this case, I'm not asking you to find where it's discontinuous. I'm asking you to find what a value would make this function continuous, because for most values of a, if I just picked a random value of a, odds are that this function would end up having a jump at x equals 1. So I want to find the single value of a that would make the left side and the right side meet up at the exact same point. To visualize what's going on, I know the right side, x squared, is going to be a parabola, shifted up 4, and it's going to be stretched vertically a little bit, but I'm only going to graph the portion to the right of x equals 1. And what I would end up having, of course, the full parabola would come down to 4 and all the way back up, but the portion to the right of x equals 1 would start at, I believe that would be 7, and then would just open up. Now the question is for the top function. Here we have a line, a linear function, because it's x to the first power. Y-intercept I know is going to be 5, but the question is, what's the slope going to be? Depending on that a value, if that a value is positive, maybe I have a negative slope, or if that a value is negative, I would end up having a positive slope. But there's only one particular a value that would make that slope be such that it matches up perfectly with the quadratic at x equals 1. So that's going to be my question, is what must that a value to give me this exact graph? Well, it comes down to that first part of the definition. Piecewise functions, I'm always going to focus on the first part of that definition. The left hand has to equal the right hand limit. The limit has to exist, so the left hand has to equal the right hand. So what I'm going to do is I'm going to evaluate the left hand limit, evaluate the right hand limit, and I'm going to figure out the a value that would make those two limits equal. So left hand limit is just a matter of taking the 1 and plugging it in for x. When I plug in 1 for x, I'm left with 5 minus 4a. Right hand limit, on the other hand, plugging in 1 for x is going to give me exactly 7. So now I have an equation that I can solve to figure out what the a value must be for the left hand limit to equal the right hand limit. Subtracting 5 from both sides, dividing by -4. As long as the a value is exactly -1/2, then this is going to be a continuous function. Any other value, it would be a discontinuous function because it would cause a jump. Using that same technique, try this one out. Pause here, play when you're ready. So once again, the key is left hand has to equal the right hand. So plugging in -2 to the left hand, I'm going to get -16. Plugging in -2 to the right hand, I'm going to get -4a minus 4a. Combining like terms on the right hand, I have -8a, divide by -8, a is exactly 2. As long as the a value is 2, I have a continuous function. Anything else, it will be discontinuous. Here's something the same but slightly different. Feel free to give this one a try. Pause here, play when you're ready, or pause here, get stumped, and play when you're not ready. This type of piecewise functions describes a situation where, consider I have a graph, and it's continuous everywhere except at a particular point, at x equals a in this case. The graph is not defined, but is defined at some separate point at a different location. Now, I'm not saying that the graph has to be below the point. I'm just giving a random example of what this type of piecewise function would describe, where I have a hole at a particular point, and then at that particular x value, I have a defined value somewhere other than the actual graph. What I'm trying to do is figure out what that a value would be such that this graph doesn't exist down here, but it actually exists at the exact same point as the defined value. So it's not a question of whether the limit exists. The question is whether the limit equals the function value. So here I'm going to focus on the third part of the definition. Does the limit, at what would be the value of a where the limit has to equal the function value? So starting with that and setting up my equation, I know the limit as x approaches a of f of x has to equal f of a exactly. Well, I know f of x can be described as x squared minus a squared over x minus a, and I know f of a, the exact value at a, is 8. Now the next thing I'm going to do is I'm going to recognize I have a difference of squares. X squared minus a squared is really x minus a, x plus a, which allows me to cancel out the x minus a, leaving behind a simpler limit question, limit as x approaches a of x plus a equal to 8. Apply the limit, combine like terms, and divide, and we see as long as the a value is exactly 4, then the limit is going to equal the exact value of the function. Otherwise, we're going to get that situation where the limit exists, the function exists, but the limit does not equal the function. One more. Pause here, play when you're ready. So here we have a problem similar to the last one, where it's not an issue of left hand, right hand, but it's an issue of the limit has to equal the exact value of the function. So I'll set it up as the limit as x approaches 0 of f of x has to equal f of 0. Since my defined value at x equals 0 is going to be 3a minus 2, I'll use that on the right side, and then a sine of x over x on the left side for my limit question. Now here I'm going to remember something from the first lesson. Sine of x over x, that looks familiar. Well, the limit as x approaches 0 of sine of x over x is and always will be 1. So then this limit side will simplify just to a. On the right side, I still have 3a minus 2. I can now solve for a. Subtracting 3a on both sides, dividing by -2, a equals 1.